Okay, hello everyone. In this video, I would like to show you how to create a model of a catchment stormwater pond system for controlling stormwater using the QAquifolium program. So let's get started. First I want to add a few plugins that we're gonna need. So I'm gonna go to preferences and then add plugins. And the plugins, I'm using a Linux machine, I have my plugins in here, but it should be, in whether you're using Linux or Windows, you can find it under resources where the program is installed. So what I'm going to do is that I will use a pond plugin. So I'm going to add that one. And then it's going to add some components for me right here. And then I'm going to also add a pipe plugin, which I'm going to need. So this is called pipe pump tank, which is going to give me some components that I'm going to be using. Okay. So I got some additional components that now I can use. Now the first thing, I'm going to do this on a step-by-step basis. So I'm going to basically create parts of the model, and then I'm going to run and make sure that it works, and then I'm going to move forward from there. So what I'm going to do is that I will first add this catchment. So I'm going to add a catchment. So this is my catchment, and I should provide some information. So let's say the Manning roughness coefficient of the catchment is 0.01. Let me expand this so that you can see the properties completely. So then I'm going to provide the slope of the catchment is let's say 0.02. I'm going to leave the initial storage to be 0. The width of the catchment, this is the hydraulic width. So I'm going to assume that this is 100 meters by 100 meters catchment. So I'm going to say 100 meters is the width, and then the area is going to be 10,000 square meters, and then the mean elevation of the catchment, I'm going to keep it at 0. Okay. Now one more thing that I need to add is I need to add a precipitation to the catchment. So the way that works is I first need to add precipitation as a source. So I'm going to go here and click on basically precipitation right here, and that will add a precipitation item under the sources. And then what I can do is I have this file, the precipitation file that is that I've already prepared. So I'm going to use that one. So I'm going to just click here and then go to, I have my precipitation file saved actually right here. So this is a precipitation file that represents precipitation data in Baltimore area from 2010 to 2012. I can also check the precipitation data to make sure that it's fine. So you can see the precipitation intensities throughout the 2 years period right here. And then now what I can do is that I can go here and add precipitation. So all I do is that I click here, and since I only have one source, it's going to be automatically selected. So this is called precipitation 1. Of course, you can change the name to anything you want, but I'm going to keep it as precipitation 1. Okay, so that's what I have now. The other thing is that if I want to run this, I need to run it during the time where I have the precipitation data available. So I'm going to change the simulation period. I'm going to go to settings, general settings, and then here I have first simulation end time and then start time because they're sorted based alphabetically. So the end time is going to be 2012, and the start time is going to be January 1st, 2010. And okay, now I'm going to save this. So let me save it in, I'm going to save it in my documents, and I'm going to call it stormwater system. And now I can run the model. Nothing interesting is going to happen, just that you have rain on our catchment, and then since water is not allowed to flow anywhere, it's going to just accumulate in our catchment, and the water depth is going to increase. So let me run it. It should be relatively fast. So nothing complicated, and this simulation is now done. Okay. Now let's check the results. So what I can do is that I can look at, let's say, water depth, for example. And as we expect, the water depth is just increasing as precipitation is happening and water is not flowing anywhere. You can also look at, I don't know, storage and other things. So now next, what I want to do is that I want to now add this pond, and then I will allow water from the catchment to flow in the pond. So I'm going to add this stormwater pond right there. I'm going to make it smaller, and then let's set some of the properties for the pond. So now I can provide precipitation on the pond too. But for now, let's assume that precipitation does not happen on the pond, or is insignificant in the pond. So I'm not gonna do that. So I'm gonna assume that the main precipitation happens only on our catchment. Then so for a pond, what we provide is that we provide some sort of a rating curve that give us storage as a function of depth, right? So basically, what I'm gonna do here is so the exponent is called beta, and it's equal to 2. So exponent of 2 is valid when our area is actually linearly increasing with depth. Okay, so the surface area is actually linearly increasing with depth, and that's what we're going to assume. And then let's say the coefficient is 100. Okay, so the coefficient of 100 means that if I have 1 meter depth of water in my pond, the volume is going to be equal to 100 cubic meters. Then and that's pretty much it. And then the bottom elevation, just it doesn't really matter, but I'm going to make the bottom elevation be 1 meter below the catchment. So I'm going to change it to -1. And then all I have to do is I have to connect my catchment to the pond to let the water from the catchment to go to the pond. So for that purpose, I'm going to use this connector called catchment link. So and then I'm going to connect them, and basically there's no properties for the catchment link. It's going to take all the properties essentially from this catchment, right? So that's what we have. So second stage of our model. I can again run and see what happens. So I'm going to save this again, and then I'm going to run it. Okay, the simulation is done. Now let's look at some of the results. So I want to look at the flow that goes to the pond. Now, because of the fact that basically the way this link is designed is that it only depends on the flow, only depends on the hydraulic head of the catchment and not the pond. So basically, we're going to keep on having flow into the pond, even though the hydraulic head in the pond at one point will exceed the hydraulic head in the catchment. But the way this catchment is formulated, if you look at the formula, you'll see that it only determines the flow based on the catchment property. So let's look at the flow. So this is the flow that we had, the runoff that we have that is generated from our catchment and is flowing to the pond. I can look at the water depth in the pond. So I can look at the depth, and as you expect, it's increasing. It's increasing to a kind of an insane value because we are not allowing any flow to basically or water to flow out of the pond. We can also look at the area or storage. So we can look at storage, we can look at the surface area. So this is the surface area of the pond, and it's increasing to around 2,000 square meters. So now I can also look at the storage, let's say in our catchment, and you can see that it's not increasing anymore continuously. It's basically increases when it rains and it goes back to 0. Now next thing I want to do, I want to let the water to overflow from my catchment to a receiving water. So let's say this receiving water is I don't know, a stream, but then what I'm going to assume is that this is going to serve as our boundary condition. So I don't want the head of the receiving water to change as a result of water that basically flows from our system into it. So I'm going to use this fixed head component. So this is something that can receive water without its hydraulic head changing. So I'm going to add this here. So this is going to be our receiving water, and then I can use, now for the receiving water I need to basically specify a hydraulic head. So I'm going to say that the hydraulic head is -2. It probably doesn't affect our results because again what I'm going to use for flow from pond to the fixed head is going to only determine the flow based on the condition of the pond and not the downstream boundary. But I'm gonna need that hydraulic head for a purpose later on. So now what I'm going to do is that I want to basically use a V-notch weir for controlling the flow from the stormwater pond into this receiving water. So I'm going to pick this connector, and then I'm going to connect my pond to the fixed head. Now what I can do is basically this weir has some parameters. It has an exponent beta, and then it has a coefficient alpha. So the flow is determined as essentially based on the hydraulic head of the upstream according to this equation right here. And then I have a crest elevation. So let's say what I want to do is anytime the water depth in the pond goes above 0.5, which means the elevation of -0.5 because the bottom elevation of the pond was at -1. Anytime that happens, I want to have flow, and then I want to set this alpha to be 1000, which is kind of a realistic value. Okay, so this is what we have, and so actually the model is ready to be run. So I'm gonna run it, and so okay, the simulation is done, and now I can look at, let's say, the flow that goes into the fixed head. So this is the flow. It's actually pretty flushy because I used a very high value of alpha. Probably I can reduce it and get a more smooth curve. And then we can look at the storage, for example, in our pond, and this is what, so storage remains around this value, and then anytime the storage goes beyond, let's say, around 30, we have overflow. I can, maybe I can use a smaller value so I'm going to use a value of 200 for my alpha, and then I'm going to get a more smooth response. Okay, so this is the system. Now what I want to do is that I want to no let's by the way check our flow from the pond. So now as you can see it's a little kind of smoother still. You know, the flow values are smaller, but I can reduce the alpha value and get a kind of more consistent. But we don't expect overflow to happen frequently anyway. So the value of 200 is reasonable. Of course, it depends on the system that you want to model and the actual wear. But anyways, now what I want to do in realistically, what we usually have in stormwater ponds, we have some sort of either infiltration or some sort of under drain system that allows water to gradually flow from the pond to the receiving water or groundwater, as long as there is water in the pond. So even if the hydraulic head is less than the overflow level, we're gonna still have flow. So what I can do is that I can maybe use a where or something else to represent that. So another one, but then Aquifolium does not allow two connectors to be connected from the same two blocks. So what I want to do is that I want to basically sort of uh, uh, basically create another pathway. In order to do that, I'm going to use this junction. Okay, so this junction is actually a dummy thing that basically allows to connect the pond to the fixed set boundary using two links essentially. I'm going to use this rigid junction. It works better. So I'm going to use a rigid junction. I'm going to leave it here, and then I'm gonna say that because I want the hydraulic, basically water depth in the junction to stay above 0 all the time, or the pressure to remain positive, I'm going to set the elevation to be -2 so that it's below the pond. And then what I will do is that I will connect. I can use a V-notch wear to, I don't know, represent our under drain system. So I'm going to use a V-notch wear again and then connect the pond to the junction, and then here the crest elevation is going to be -1. Okay, that's the bottom elevation of our pond. The reason for that is that I want this flow to happen all the time, even if you have a very little amount of water in the pond. And then the coefficient, I'm going to make it, let's say, a smaller value because I expect this flow to be smaller. So I'm gonna use a value of 20. Now for junction to the fixed head, I can use any link, but I'm going to use let's say a two-way pipe. So I'm going to connect my junction to the fixed head using a two-way pipe. And then let's say this pipe has some parameters. It has diameter, it has a Hazen-Williams coefficient, and it has a length. So I'm going to say the diameter is, let's say, 5 centimeters. And let's say the pipe length is 10. And now I think everything should be set, and I can run this. Okay, so now let's look at the result. Let's see how often now our basically stormwater pond overflows. So it still overflows substantially because of the fact that probably the wear that I put in place here is not, basically doesn't allow that much water compared to the flow that goes into the pond. If you look, we're talking about something of the order of 2,000 cubic meters per day, but this wear only allows something around I don't know, 150. So we still have some overflow. Now what I can do is that I can maybe increase the size of this under drain pipe to allow more water to flow through, maybe to 100, and run the simulation again. And what we see is the flow here should have increased. It has increased by, should be roughly a factor of 5 compared to the previous simulation. And then here we can look at the overflow, and so you have less incidence of overflow. Still it's substantial, but that gives you the idea. Thank you very much for watching. Please look for my other videos on QAquifolium, and feel free to leave comments if you have any questions or comments.